Welcome, friends, to the next installment of our Top 10 Brightest Stars. I'm Dr. Jim Daly, and tonight we're going to be talking about the star Vega. We open up tonight's video looking due south. We see beautiful early twilight just after sunset. We see the waxing crescent moon in plain view. And what we're going to do is we're going to let the sky slowly drift to the west and watch the prominent stars of summer come into view. Looking due south. The southern sky in the summer months is the most spectacular, okay? Because if we were to travel to a remote location, get away from the city lights and light pollution, you would see the galactic center in full view. We can do that. We can simulate that here with stellarium by taking away the atmosphere. Okay, here's the Milky Way's galactic center, and we have Scorpio with Sagittarius, and the bright star, red supergiant star Antares, which is going to be next in the third in our list of top 10 brightest stars. That's coming up in the next video. Tonight we're going to be talking about the star Vega. Okay, let's put the atmosphere back, come back to our home planet, put the Earth atmosphere back, and we're going to let the sky drift forward just a little bit longer. See how the sky changes. The galactic center is coming into view, the Milky Way. If you have a pair of binoculars, this is a breathtaking vista. Take a look at your binoculars, sweep this whole region of the sky. It's especially stunning. If we look high overhead tonight, we're going to see the summer triangle, Vega, Deneb, and Altair. These will be our candidates for our list of top 10. Tonight we're going to take a look at Vega. Okay, the summer triangle is another one of these patterns in the sky that we call asterisms. Last week, the last installment, okay, we looked at the star Arcturus, right, over here to the west, and we found it using the Big Dipper, another asterism, not a constellation in its own right, but a recognizable pattern of stars on the sky that helps us navigate to other objects of interest. In that case was Arcturus. In this case, we have the summer triangle high overhead, Deneb, Vega, and Altair. Okay, in three distinct constellations. Vega is the brightest star, principal star in the constellation of Lyra, the Harp. Okay. According to Greco-Roman mythology, well, let me just go back to our article. I describe it clearly here. According to Greek lore and mythology, Orpheus, a legendary musician, poet, and prophet, was transformed into a swan, Cygnus, as we just saw, and his murder, okay, and is said to have been placed in the sky next to his lyre, Lyra. According to the myth, Lyra is said to have been made from a tortoise shell and is the first lyre ever produced. It has also been said that Orpheus' music was so beautiful and enchanting that even inanimate objects such as trees and rocks were charmed and came to life. The remainder of Orpheus' story is a classic example of a Greek tragedy. It is said that he spent the last years of his life strumming his lyre while aimlessly wandering the underworld, pining away for his lost love, Eurydice. Okay, and we look high overhead. We see where Lyra is placed right next to the Northern Cross or Cygnus. Okay, the Northern Cross, I should add, is also another one of these asterisms. Okay, in a larger asterism of the Great Summer Triangle, we have the Northern Cross. Obviously, it's a cross, right? You see that. Okay, but the wings of the extensions of the cross here are the wings of the swan, and this is long neck, ending down here in the star Albireo. Okay. Okay, let's get back to focus on the star of interest, which is Vega. Made famous in the full feature-length movie Hollywood production of Contact. Matthew McConaughey and Jodie Foster are the principal characters, and it's about a fictional contact, hence the name of the movie, with an advanced civilization in orbit around and on a planet in orbit around the star Vega. Okay, as we'll come to learn soon, that's probably not a likely scenario, because Vega, with its higher luminosity and higher mass than the Sun, is probably not going to live long enough to have life emerge and thrive as it did here in our solar system with the Sun as our principal star on our planet Earth. Okay, as we did in the previous video about Arcturus, let's take a look at Universe Sandbox. This is a very powerful tool that allows us to simulate astrophysical scenarios and ideas that we would not normally be able to do and observe in nature. Here we see, set against the backdrop of the galactic center, as we saw here in Stellarium, down here, okay, we have our solar system. The major planets in orbit around the Sun at any given moment in time. Okay, the Sun is by definition a one solar mass star. If we were to replace the Sun, as we did in the previous example about Arcturus, the solar system would change. The entire solar system itself would be affected by that change. So let's see what would happen if we replace the Sun here. Let's choose the Sun. We're going to select the Sun, and then we're going to replace it with another star. And that other star is going to be the star Vega, right here. Replace. Click replace, and right away we're going to see a change. Look at how everything speeds up. Why did it speed up? Let's zoom in and take a closer look. Look at how quickly Mercury, well, Mercury's always been fast. Mercury is named in honor of the Greek god Mercury, the messenger. Why was he named such? Because he's very fast and he delivers the messages very quickly. But now he got a boost in speed. He's hypersonic now, as the closest planet to the star, in this case Vega, having replaced the Sun, is going to orbit this star much quicker and much faster than it did previously with a one solar mass star. Vega is over two solar masses. Now there's a certain astrophysical principle known as the mass-luminosity relationship, where the luminosity of a given star varies as the fourth power of the star's mass. So if the Sun is 1 and Vega is 2 solar masses, 2 to the fourth power is 16. So any given planet will receive 16 times the amount of energy at any given moment than it did with the Sun. Okay, now how does that increase in energy, how is that going to affect the living conditions, for example, on our planet Earth? Now we're going to wait in the simulation until Earth comes around, and we're going to pause it at its closest approach. And we're going to take a look at the temperature. We're going to do another go at that. We're going to pause it a little bit earlier. Right here, take a look. We're going to select the Earth. Okay, we can see right away. We can see that the Earth, the prevailing temperature on the Earth is 872 C, or 1600 degrees. If we replace the Sun with the star Vega. Lead melts at 700 degrees. So this is over twice the melting point of lead. Okay, clearly you would have to be much further away than the planet Earth is today to have life evolve and thrive. Let's take a look at Mars. What is the prevailing temperature on Mars with this, having replaced the Sun with Vega? Let's take a look. We're going to get Mars a little closer. Take a look. Mars is going to be very hot too. Even at Mars, it's 623 C, or 1100 degrees. Steel at this temperature becomes pliable, molten a little bit with a little hotter temperature. So if we replace the Sun with the star Vega, we'd have to actually move out to, let's take a look at Jupiter, perhaps out here, 23C, 27C, or a comfortable, or a balmy 81 degrees. So in order to have life evolve and thrive, we'd have to be at a distance of the planet Jupiter, or 5 times the distance the Earth is from the Sun right now, in order to have life get a foothold and survive, given the extreme temperatures that we'd experience, having replaced Vega, having replaced the Sun with Vega. All right. Also, take a look at how fast everything's moving. Zoom in. Everything's much faster. So clearly, the star Vega would not be a good candidate to look for signs of an advanced civilization. Now, it also needs to be mentioned that because the luminosity of Vega is much higher, much greater than it is with the Sun, it's going to live much shorter life. About 1.5 billion years is the productive lifetime of a star like Vega, about 2 solar masses. For stars like our Sun, it's upwards above 10 billion years. Okay, as it is now, it's 3.8 billion years since the first life formed on the Earth. It took 3.5 billion years for us to get where we are now in the evolutionary timeline. Okay, it took 800 million years after the Earth formed, 4.5 billion years ago, for that first life to evolve from complex amino acids and hydrocarbons in the ancient seas of the Earth. And 3.5 billion years later, we arrived at the pinnacle, or the dominant species on the planet. So in 1.5 billion years, that's the entire productive lifetime of a star like Vega. It's not going to happen. Life would be not enough time for advanced life to gain a foothold and thrive in an environment such as would be produced around Vega. All right, let's get back to the to Stellarium for a moment. Take a look. Go back high overhead. We're going to bring up the constellation of Lyra again. Okay, we're going to zoom in on Lyra. This is a binocular field view, what you might see in a nice pair of binoculars in the night sky. I should point out here also, this is a telescopic view of Vega. As seen, I produced this image of Vega a little while ago with my 20 centimeter telescope. It should be noted also that Vega appears so bright in our sky because it's relatively close, only 25 light years distant. So the light we see tonight left that star 25 years ago. So those of you who are now 25 years old, the light left that star that you see tonight when you were born, the day you were born. Between these two stars, Sulafat and Chelyabinsk, we have another object made famous by Charles Messier in his catalog of 110 non-cometary objects, known as Messier 57, or the Great Ring Nebula in Lyra. Now, it should be mentioned, since we're talking about, briefly talking about the evolution of stars, the Sun, Arcturus, is, we mentioned in the previous video, is an evolved giant star, has evolved off the main sequence. It has consumed all its complement of hydrogen fuel in its core, and is now using helium as a fuel to sustain the nuclear fusion reactions going on in its core. That reaction is producing carbon and oxygen. Okay, that's what will happen to the Sun, and what results as the end state for stars like Arcturus and the Sun, and perhaps like Vega, will be this object, such an object as this, Messier 57, or the Great Ring Nebula in Lyra. A wide field view of that ring nebula. See this little red donut right here? A little red smoke ring right here. Let's zoom in a little bit. Okay. I produced this image of the ring nebula with my 15 centimeter telescope a number of years ago as a wide field view, comparable to what you might see in a pair of binoculars. In a large telescope such as the Hubble telescope, this is what we see here. Okay? M57, Messier 57, is an example of what we call a planetary nebula. A planetary nebula is the end state for stars like our Sun. Stars like Vega, perhaps, like Arcturus, which was a one solar mass star. When the core of the star can no longer use the product of the previous generations of nuclear burning. In this case, for the Sun and Arcturus, and also for Vega perhaps, carbon and oxygen, what happens is the outer layer of the star keeps expanding, becoming more rarefied and tenuous, until it just basically blends in with the vacuum of space. Okay, we call that a planetary nebula. It has nothing to do with a planet. In a small telescope, such as the earlier telescopes developed 100, 200 years ago, early generations of telescopes, these objects look like planets because of their circular shape, hence the term planetary nebula, but they have nothing to do with planets. At the center of this nebula, which is a Latin term, means cloud, we see the central white dwarf star. That's the end state. That was the nuclear cauldron, the core of the star, that was, through nuclear fusion, was producing hydrogen, was using hydrogen as a fuel, transmuting it into helium. The helium runs down in three steps to produce carbon and some oxygen. That star, this white dwarf star, although very hot, is no longer producing energy. It's just cooling off. Over many billions of years, it will continue to cool and fade to black. In the meantime, the ionizing radiation from that white dwarf star is providing the energy that's causing this ring of gas, which used to be the outer shell or the outer layer of the star's atmosphere, to glow in these beautiful colors. Okay, this is a view through the Hubble telescope. Through a pair of binoculars, it would look something like this here. Okay, this is a wide field view. Much in the same way as you would see with that same pair of binoculars, you might see the constellation of Lyra. The Ring Nebula, or M57, is located right here between these two stars. Another interesting aspect to Vega is that Vega, in approximately 12 to 13,000 years, will become our pole star. Currently, Polaris is our pole star because of because of the Earth's wobble on its axis. A very long-term perturbation in the Earth's motion causes it to wobble with its polar axis pointing, right now pointing towards Polaris, but in 13,000 years hence, it will be pointing towards the star Vega in the year 14,000. Okay, as illustrated in this diagram. Okay, right now, in the 21st century, we're pointing to Polaris. We call this the precession of the equinoxes. And as such, the equinox, the vernal equinox, and all these seasonal points will process with the Earth's precessional wobble. It's a very long-term perturbation, a very long-term change, or even over the span of a human lifetime or even a millennium, you're not going to see much of a change. In 12,000 years hence or so, Polaris will have changed. It will no longer to be the North Star, it will be the star Vega. The Earth's polar axis will be pointing towards Vega. Here we see the plane of the Earth's orbit around the Sun. We call that the plane of the ecliptic. Okay? 12 to 13,000 years. Vega will be the pole star. Currently it's Polaris. Okay, I'd like to also briefly mention our article that talks about this. It's the latest article here about our top 10. The top 10 brightest stars and where they are. We're presenting Vega this time with this installment. Okay, talk about Lyra and discuss some of the lore and briefly mention the Ring Nebula down here. All of these topics such as this, the top 10 brightest stars, which seems to be a favorite. We also have another article that we published called The Top 10 Questions in Astronomy. And that's out there too. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized. If you found this video helpful and educational, please like, subscribe, and share. Also, why not consider supporting us on Patreon? Head over to our homepage, astronomyforchange.org, click Support Us via PayPal or Patreon, and head on over to our Patreon page and choose a membership level suitable for you. Every little bit helps us produce the great content and further our mission. Also, why not consider becoming a member? Membership is free at Astronomy for Change. Head on over to our homepage, choose the membership link here, click it, put your name and your first name and your email, and you'll be added to our list. You'll receive a comprehensive digest of all our videos and articles and all our great content. Joining and becoming a patron, helps us grow and improve and more fully realize our mission. Thank you. This is Dr. Jim Daly for Astronomy for Change. Until the next video, please stay well and keep looking up.